All right, hey everyone, I am now back in Nashville. So here we are right back just in the backyard of the museum up here in Fort Negley, and I just wanted to take a minute and say hi. I know it's been about a week, but I've needed most of that time to get back to a regular schedule of sleeping at night and actually being awake in the morning with the rest of my co-workers here at the Science Center. So we've been able to take a little bit of look at the data that we got last week, and we have some really exciting findings. So we've been able to measure these asteroids, even with some cloudy weather. Those telescopes were so good that we've been using on this project that we measured how fast some of these asteroids were turning. At this point, we've measured hundreds of asteroids out in Jupiter's orbit, and we've been taking a look at how long they take to turn, you'll remember. So as we watch how long these asteroids take to turn, we've noticed that most of them are turning very, very slowly. Take a look at this asteroid that we measured just last week. Now you'll notice we just have one peak and one trough on this graph, which means this is only half a rotation. But for that half a rotation, you can see it takes just about 14 and a half hours to turn around. So 14 and a half hours to turn from front to back. We need to double that for the full turn. So if my math is right, that means we're looking at just under 29 hours to make a full revolution. So this is a very, very slow rotating asteroid, and what we've noticed is almost all of the ones we've seen have been slow rotating. We've been having a lot of trouble finding anything that turns quickly. So what can we learn from that? Well, one possible conclusion that we might get as we study this data further is that when we look at these slow rotators, they might be made of something a little bit more fragile or something a little bit more loosely held together. So you'll remember that potato idea, right? These asteroids are turning in space. If asteroids are made of different materials, then they'll hold themselves together a little bit better or maybe a little bit more poorly. So imagine if we have a turntable. I'm going to listen to some vinyl, be a nice hipster, and I'll take this and just crank up the speed. Now imagine if I put a piece of clay on that turntable. That clay is going to stay together. Imagine if I put a pile of sand on the turntable and crank that speed up one more time. The sand is going to fly apart. So asteroids aren't exactly made of clay or sand, but one question we have is if they're made of rock or ice. Rock would hold together a lot more strongly. Ice would break up a little bit more. So if that rock holds together more strongly, rock could rotate quickly. If we're not finding any asteroids rotating quickly, these asteroids might not be made of rock. They might be made of ice. Now, why does that matter? Well, if these asteroids are made of ice, then they probably didn't form the same way the main asteroid belt between Mars and Jupiter did. Now, we have icy bodies in our solar system, especially a lot of objects out in the Kuiper belt or out in the Oort cloud. So if these are icy asteroids, they may have actually come to be where they are from somewhere else in the solar system rather than forming in place. So this is just one piece to a much, much, much bigger puzzle of how we explore the solar system. And for now, I am back to work. I get to explore our solar system survey right here at the Science Center. So if you'll excuse me, I've got some planets to explore, and I hope you'll come join me soon.